Welcome to part 3 on rational functions. We're now going to look at how we can define asymptotes of a rational function based on the degree of the numerator and the denominator. Here we have r of x equals a polynomial in the numerator and a polynomial in the denominator. We are going to compare the degree of the numerator with the degree of the denominator. The numerator's degree is n, and that's convenient because if you think of the numerator as starting with the letter n, numerator, you can kind of keep track of these rules as we go. The denominator is degree m. And so now we're going to look at the rules for finding horizontal and vertical asymptotes. The vertical asymptotes of the polynomial r of x are the lines x equals a, where a is a 0 of the denominator. So these would give you all your vertical asymptotes. And I'll just sketch a few in. We could have 1, 2, or more, based on how many zeros are in the denominator. Now let's say that we also have m greater than n, or n is less than m. Then r has horizontal asymptotes at y equals 0. That would be along the x-axis. So this is when the numerator degree is less than the denominator's degree. If n equals m, then r has horizontal asymptotes at the coefficients. So this could either be above or below the x-axis. So it's based on the leading coefficients. And there was a video earlier where I showed you an example of that. I believe it was at 3. So this is where you have a coefficient in the numerator divided by a coefficient in the denominator, and then it gives you that value for that horizontal asymptote. If n is greater than m, then r has no horizontal asymptotes. If you think about it, the numerator will be bigger than the denominator, degree-wise, and r has no horizontal asymptotes. But for every degree higher the numerator is from the denominator, and this follows from part 3, if n equals m plus 1, so the numerator is 1 degree higher, then you will have a linear, diagonal, or oblique asymptote. If n equals m plus 2, then it's not going to be linear anymore, because now the degree of the numerator is 2 numbers higher than the degree of the denominator. That would be a parabolic asymptote. And you won't see this very often, but you can have parabolic, you can have cubic, you can have quartic, etc. asymptotes, because you just have to make sure that the degree of the numerator is higher by that many numbers. So for linear, it would be 1 degree higher in the numerator. For parabolic, it would be 2 degrees higher. For cubic, it would be 3 degrees higher. I think you get the idea. So now let's take a look at an example. In the first example here, we have f of x equals 2x over 3x squared minus 3. So if we compare the degree of the numerator with the degree of the denominator, the degree of the numerator, n, is less than m. So this gives us a horizontal asymptote. I'll call it HA for short. Horizontal asymptote at y equals 0. We also need to check for vertical asymptotes. I'll call those VA for short. and we need to find out where they will be. We'll have x equals some value, and there might be more than one. So when this happens, we set the denominator equal to 0 and solve for x. 3x squared minus 3 equals 0. Solving for x squared, we have x squared equals 1. So that means I will have vertical asymptotes at plus or minus 1. Because if I take the square root of both sides, and it's an even root, I'll get the plus or minus. The square root of 1 is 1. So to sketch this, the vertical asymptotes will be at plus or minus 1. And the horizontal asymptotes will be at 0. Now, depending on where this function is positive and negative, we'll define where the polynomial or the rational function hugs the asymptotes to either positive or negative infinity. Let's take a look at B. In this scenario, the degree of the numerator equals the degree of the denominator. Remember, when n equals m, we take the coefficients of the numerator and denominator. So there will be a horizontal asymptote at y equals 2/3 because of the degree of the numerator matches the degree of the denominator. There will be a vertical asymptote at x equals plus or minus 1, just like before. And if we wanted to be even more curious, this isn't part of the assignment, but if you wanted to find the roots of this rational function, the roots are based off of the numerator, so we would take 2x squared and set it equal to 0. That means x has a root at 0. The same would be true of part A. We could say that there is a root for this rational function at 0. Let's take a look at the last example here. In this particular situation, the numerator is greater than the denominator. This means there is an oblique asymptote at y equals the quotient. Now, that seems weird, and so we would actually have to take the numerator, 2x to the third, and divide it by the denominator, 3x squared minus 3. So I'll extend my terms out, plus 0x squared plus 0x plus 0, just so I have my place values. And I cannot use synthetic division because this is degree 2. So you still have to remember your polynomial long division. Take the first term of the dividend, 2x to the third, divide it by the first term of the divisor. That gives me a 2/3 x, and I put that in the quotient. Now I multiply that to each term in the divisor, and that will give me 2x to the third minus 6/3 x. Well, 6/3 is minus 2, so minus 2x, and now we'll change the sign. The first two terms add to 0. I drop down the 0x squared. 0x plus 2x is plus 2x. Drop down the plus 0. So now I have 2x as the dividend. Divide it by 3x squared. That's going to give me 2/3, and the x will be in the denominator. So it would say as x approaches infinity, 2/3x approaches 0. And so I am just going to write this as 2/3 x. So my y equals quotient is y equals 2/3 x. And so this will be the oblique asymptote when the numerator degree is larger than the denominator's degree. Notice that it is linear because the degree of the numerator is 1 degree higher than the degree of the denominator. We also have vertical asymptotes at x equals plus or minus 1.